On July 1st, 2025, NASA discovered something moving through our solar system that produces metals the same way a factory would. And that's just the beginning of why scientists are losing sleep over this thing. This object is called 3I divided by Atlas. It's the third interstellar visitor we've ever detected, and it's currently racing past Mars at 130,000 miles per hour. But here's what makes this different from anything we've seen before. The chemistry coming off this thing shouldn't exist in nature. The size doesn't match what we thought was possible for interstellar objects. And the age? We're talking about something that might be older than our entire solar system by billions of years. By the end of this video, you're going to understand why this ancient wanderer has scientists questioning everything they thought they knew about the universe, and why we only have a few months to study it before it disappears forever. Let me paint you a picture of what's happening right now. There's a comet passing through our solar system. Nothing unusual about that, right? We see comets all the time, except this one didn't form here. It came from somewhere else in the galaxy. Somewhere incredibly old. Somewhere that operated by completely different rules than anything we understand today. And the clock is ticking. Every single day, this object is moving further away from Earth. By March 2026, it'll cross Jupiter's orbit and begin its final exit from our solar system. Once it leaves, it's gone forever. We will never see it again. No future generation will have the chance to study it. This is humanity's one shot to examine something that carries information from an era of the universe that no longer exists. Think about that for a second. This isn't like studying an ancient artifact buried in the ground that we can excavate anytime we want. This is a messenger from the early cosmos that's only passing through once. If we don't figure out what it's trying to tell us now, that knowledge dies with its departure. But here's where things get really unsettling. The more data we collect on 3I divided by Atlas, the less sense it makes. Every telescope that points at this thing discovers something new that contradicts what we thought we knew about space. NASA, the European Space Agency, observatories around the world, they're all watching this object. And what they're seeing is making them seriously uncomfortable. Let me give you just one example before we go deeper. Remember how I mentioned this thing produces metals? I'm not talking about trace amounts. 3I divided by Atlas is spewing out pure nickel vapor at a rate of about 5 grams per second. Over the course of its approach to the sun, that adds up to roughly 0.5 metric ton of nickel waste. Now, nickel exists in space. That's not the weird part. The weird part is that nickel and iron always appear together in natural cosmic objects. Always. They're forged at the same time in exploding stars. They're bonded together in asteroids and comets. Finding one without the other is like finding water without hydrogen. It just doesn't happen in nature. But 3I divided by Atlas is producing abundant nickel with minimal iron signatures. Harvard astrophysicist Avi Loeb put it this way: nickel without iron is a signature of industrial production of nickel alloys. Industrial production. Let that sink in for a moment. We're not talking about aliens here. Not yet, anyway. We're talking about chemistry that looks manufactured. Chemistry that doesn't fit any natural process we've ever observed in the universe. Chemistry that, according to our current understanding of stellar evolution and nucleosynthesis, shouldn't exist. And that's just one of the mysteries surrounding 3I divided by Atlas. We haven't even touched on its age, its size, its bizarre behavior, or the implications of where it came from. So here's what we're going to do. We're going to go through every single anomaly that makes 3I divided by Atlas so disturbing. We're going to look at what the data actually says. We're going to explore what it means for our understanding of the universe. And by the end, you're going to understand why the discovery of this object might be one of the most significant astronomical events in human history. But first, we need to understand how we even found this thing. Part 1. The discovery. The Atlas Survey Telescope sits in Hawaii, scanning the sky every night for objects that might pose a threat to Earth. It's part of NASA's Planetary Defense Program. The whole purpose is to find asteroids and comets that could potentially hit our planet, giving us as much warning as possible. On the night of July 1st, 2025, Atlas picked up a new object. At first, it looked like just another comet, nothing special. The team logged it, calculated its orbit, and prepared to move on. But then something caught their attention. The orbit wasn't right. When they ran the calculations, they realized this thing wasn't following an elliptical path around the sun like normal solar system objects do. It was following a hyperbolic trajectory. That means it's moving too fast to be gravitationally bound to our Sunday. It came from outside our solar system, and it's going to leave our solar system. This was only the third time in history we detected something like this. The first was Oumuamua in 2017. That weird cigar-shaped object that tumbled through our solar system and sparked all kinds of debate about what it actually was. The second was 2I divided by Borisov in 2019, which was more clearly a comet. And now we had a third visitor, 3I divided by Atlas. The 3I means third interstellar object. The Atlas comes from the telescope that discovered it. Within hours of the discovery, observatories around the world started pointing their instruments at this new visitor. And almost immediately, they realized they were looking at something extraordinary. The Very Large Telescope in Chile was one of the first to get detailed observations. They used spectroscopy, which is basically analyzing the light coming off the object to figure out what chemicals are present. And that's when they detected the nickel signature I mentioned earlier. But they also found something else. Or rather, they didn't find something they expected to find. Where was the iron? They checked their instruments. They ran the analysis again. They compared it to other observations. The result was the same. Tons of nickel. Almost no iron. The team described it as extremely puzzling. That's scientific speak for, we have no idea what we're looking at. But that was just the beginning. The James Webb Space Telescope turned its powerful infrared instruments toward 3I divided by Atlas. Webb can detect molecules and compounds that other telescopes miss. What it found was equally baffling. 3I divided by Atlas has one of the highest carbon dioxide to water ratios ever recorded in any comet. Most comets are basically dirty snowballs. They're made primarily of water ice with some other stuff mixed in. When they get close to the sun, the ice heats up and creates that beautiful tail we associate with comets. But 3I divided by Atlas is different. This thing is absolutely loaded with carbon dioxide. The ratio is 7.6 parts CO2 to 0.3 parts water. That makes it a 4.5 sigma outlier from normal comets. In statistics, that means it's so far outside the normal range that the probability of this happening by chance is incredibly small. Think of it this way. If you measured the height of 1 million people and found one person who was 9 feet tall, that would be a statistical outlier. 3I divided by Atlas is that 9-foot tall person in the world of comets. The Spheric Space Telescope, which specializes in mapping the sky in infrared light, detected a massive CO2 coma around 3I divided by Atlas extending at least 348,000 kilometers. That's almost the distance from Earth to the Moon. This thing is wrapped in a huge cloud of carbon dioxide. Meanwhile, water signatures remain surprisingly weak despite the comet getting closer to the Sunday This is completely backwards from what we expect. Water should be dominating. CO2 should be secondary. But 3 I divided by Atlas flips that script entirely. So already, within weeks of discovery, we had 2 major anomalies. The nickel without iron problem, and the CO2 water inversion problem. 2 things that don't make sense according to our current understanding of how comets and interstellar objects should behave. But scientists were just getting started. As more observatories joined the effort to study 3 I divided by Atlas, the list of mysteries kept growing. The Hubble Space Telescope captured high-resolution images of the object, and that's when they noticed the anti-tail. Most comets have tails that stream away from the sunday. That's because solar radiation pressure pushes dust and gas away from the sun's direction. It's basic physics. The tail always points away from the sunday. Except 3 I divided by Atlas has dust and debris streaming ahead of it. Toward the sunday, Hubble's observations showed dust being ejected from the sun-facing side of the nucleus. But instead of forming the expected tail streaming away from the sun, much of this material was moving in the solar direction. This suggests either extraordinarily dense particles that are too massive to be affected by normal solar wind dynamics, or some other mechanism that violates conventional cometary physics. Then there was the color change. Austrian astronomers observing 3 I divided by Atlas in September 2025 noticed something strange. The object was changing color. When it was first discovered, it had a reddish tint. That redness comes from organic compounds called tholins, which form on surfaces exposed to radiation over long periods of time. But as 3 I divided by Atlas got closer to the sun and heated up, it started turning green. Green comets aren't unheard of. The color usually comes from diatomic carbon or cyanide production. But the transition from red to green suggested that heating was liberating subsurface materials that had remained frozen and pristine for an incomprehensibly long time. Materials from an era of the galaxy we can barely imagine. And speaking of time, let's talk about the single most disturbing aspect of 3 I divided by Atlas. Its age. Part 2. The Ancient Wanderer. How do you figure out how old a comet is? You can't exactly cut it in half and count the rings. Instead, scientists look at where it came from and trace its journey backward through time. Multiple independent research teams did exactly that with 3 I divided by Atlas. They analyzed its trajectory, its velocity, its direction of approach. They ran complex simulations modeling its path through the galaxy, accounting for gravitational interactions with stars, nebulae, and other massive objects over millions and billions of years. The results converged on an estimate that should make anyone uncomfortable. 3 I divided by Atlas is somewhere between 7 and 14 billion years old. Some analyses suggest it could be as ancient as the Milky Way galaxy itself. To put that in perspective, our solar system is about 4.6 billion years old. The sun formed from a cloud of gas and dust, then the planets coalesced around it. Earth is roughly the same age. Life on Earth has existed for maybe 3.7 billion years. Human civilization is about 10,000 years old. 3 I divided by Atlas predates all of that. By a lot. This object was already ancient when our sun was born. It was wandering through the galaxy when the cloud that would become our solar system was just starting to collapse. It existed during an era of the universe when everything was fundamentally different. Star formation rates were higher back then. The chemical composition of the galaxy was different. The very conditions under which objects formed were unlike anything we see today. And now this relic from that alien epoch has drifted into our cosmic neighborhood, giving us a chance to examine a direct sample of matter from the early universe. Except we don't have much time, and we don't really understand what we're looking at. The age calculation comes from 3I divided by Atlas's origin point. By tracing its trajectory backward, scientists determined it came from the Milky Way's thick disk. This is a population of ancient stars that formed during the galaxy's turbulent early epochs, when the universe was only about 20% of its current age. The thick disk contains stellar remnants from a time when the galaxy was still settling into its current structure. Stars were exploding left and right. Black holes were gobbling up material. The entire galactic environment was violent and chaotic in ways we can barely comprehend today. Objects that formed in the thick disk carry chemical signatures from that era. They're made of materials processed through those early stars. They bear witness to cosmic events that happened before our sun even existed. 3I divided by Atlas is one of those witnesses. But here's what really gets me. This thing has been traveling through space for billions of years. Think about that journey for a moment. While Earth was forming, 3I divided by Atlas was drifting through the galaxy. While the first life was emerging in Earth's oceans, this object was passing by distant stars we'll never know the names of. While dinosaurs ruled our planet, then went extinct, then mammals took over, then humans evolved and built civilizations. 3I divided by Atlas was out there, wandering silently through the void. It has survived exposure to galactic cosmic radiation for billions of years. It has endured temperatures near absolute zero. It has been bombarded by micrometeoroids countless times. It has witnessed stellar explosions, planetary formations, maybe even the birth and death of entire solar systems. And somehow, through all of that, it has remained intact, frozen, preserved, carrying information from an age we can only glimpse through telescopes pointed at the most distant reaches of the universe. Now it's here, passing through our backyard, giving us a brief window to study it. But the age creates another problem. How did something this old, this massive, achieve such an extreme velocity? Part 3. The velocity problem. 3I divided by Atlas is traveling through our solar system at an astonishing speed, about 58 kilometers per second, or roughly 130,000 miles per hour relative to the Sunday. That makes it the fastest interstellar object ever observed. To put that in perspective, most comets within our solar system move between 20 and 50 kilometers per second when they're near the Sunday. These comets are bound to the sun's gravity, following elliptical orbits that bring them back again and again. But interstellar objects are different. They aren't gravitationally bound to the Sunday. They pass through once and keep going, following hyperbolic trajectories that let them escape into deep space. The first object of this kind we discovered, Oumuamua, had a hyperbolic excess velocity of about 26 kilometers per second. The second, 2I divided by Borisov, traveled around 32 kilometers per second. 3I divided by Atlas nearly doubles that. Such extreme speed presents a real challenge for our models of how interstellar objects are formed and ejected from their home systems. When planets form around a star, leftover material, rock, ice, and dust can get flung out into space through gravitational interactions. Imagine a cosmic game of billiards. A large planet passes near a smaller body, and gravity acts like a cue ball, launching the smaller one outward. This process explains how interstellar debris can escape a system. However, there's a limit to how fast such objects can be ejected through normal gravitational scattering. For typical planetary systems, the upper bound is around 30-40 kilometers per second. That makes 3I divided by Atlas's speed 58 kilometers per second hard to explain. One possibility is that it didn't get all that speed at once. Over billions of years, it could have passed near multiple stars or massive objects, each encounter giving it a small additional boost. The cumulative effect might explain its current velocity. Trajectory data supports this idea. 3I divided by Atlas shows signs of having interacted with several stellar systems over time. But even accounting for that, the math suggests those boosts might not be enough. To reach this speed, the object would have needed either many such encounters or a few very energetic ones. Perhaps it once passed close to a binary star system, where two stars orbiting each other could have acted like a gravitational slingshot. Or maybe it passed near a stellar remnant, such as a neutron star or black hole, whose intense gravity briefly accelerated it to extreme velocity before flinging it outward. Another scenario is that 3I divided by Atlas was ejected during a violent event in its original system, something like a massive collision or an energetic stellar outburst that propelled it into interstellar space at tremendous speed. Some researchers have even considered whether conditions in the early galaxy might have allowed ejection events that don't occur anymore, processes that we simply haven't observed yet. Whatever the case, 3I divided by Atlas is pushing the boundaries of what our current models can explain. Its speed challenges our understanding of how natural forces shape and move objects between the stars. And that's the exciting part. It's a reminder that our cosmic models are still evolving, and the universe may still have a few surprises left for us to uncover. With 3I divided by Atlas, it's looking more and more like we need to seriously revise our models. Because the velocity problem is just one piece of a much larger puzzle, let's talk about size. Part 4. Bigger than expected. Early estimates of 3I divided by Atlas's size came from its brightness and some educated guesses about how reflective it might be. Based on that, scientists thought it was only a few kilometers wide large, but still within the range of big comets we've seen before. Then came higher resolution data from the Vera C. Rubin Observatory, one of the most advanced sky survey instruments ever built. It can detect extremely faint, distant objects and measure them with remarkable precision. When the Rubin team analyzed their observations, the numbers changed dramatically. They calculated that the nucleus of 3I divided by Atlas is about 5.6 kilometers in radius, making it roughly 11 kilometers or 7 miles across. For comparison, Oumuamua was likely less than half a kilometer long. 2I divided by Borisov was about 1 kilometer in diameter. 3I divided by Atlas is around 10 times larger. That size difference matters. Based on its dimensions and assuming a typical comet-like density, the object's mass comes out to roughly 33 billion tons. That's enormous for something traveling between stars. While still tiny compared to planets, it's unexpectedly massive for an interstellar traveler that somehow reached a speed of 58 kilometers per second. Here's the problem. The more massive something is, the harder it is to accelerate. According to Newton's second law, increasing speed requires force, and the heavier the object, the more force it takes. Small icy bodies can be ejected from their home systems fairly easily through gravitational interactions with large planets. But launching something the size and weight of 3I divided by Atlas to such an extreme velocity would take immense energy far beyond what typical planetary encounters can explain. So where did that energy come from? One idea is that it gained speed gradually, over billions of years, through multiple close passes by stars or other massive objects. Another possibility is that it was thrown out of its original system during a particularly energetic event. perhaps something that occurred under very early galactic conditions that no longer exist today. Whatever the mechanism, it's clear that 3I divided by Atlas challenges our current understanding of how objects are ejected into interstellar space. Its size also raises another puzzle. Larger objects cool and erode more slowly over time. They can preserve internal layers and structure far better than smaller ones. Smaller comets and asteroids, after billions of years exposed to cosmic radiation and temperature extremes, tend to break down into fragile rubble. But an object 11 kilometers wide could easily protect its inner material from that kind of processing. That means 3I divided by Atlas might still contain ancient, unaltered matter material that formed billions of years ago, preserved in its core since the earliest eras of the galaxy. If so, it's not just another interstellar rock, it's a time capsule, carrying clues about the raw ingredients of the early universe material we could never otherwise study directly. And yet, we may never get another chance to examine it up close. 3I divided by Atlas is moving fast, and soon it'll be gone from our reach forever. But before that happens, there's another mystery we have to address, one that's even harder to explain: its activity. Part 5. The early activity problem. Comets are supposed to be inactive until they get close to the Sunday. The heat from sunlight warms the ice, causing it to sublimate directly from solid to gas. That gas carries dust particles with it, creating the coma and tail that make comets so beautiful. Different ices sublimate at different temperatures. Water ice is relatively stable and doesn't really start sublimating until a comet gets inside, about 3 to 4 astronomical units from the Sunday. That's roughly around Mars's orbit. More volatile ices like carbon monoxide or carbon dioxide can start sublimating further out, maybe around 5 to 6 AU in some cases. But most comets are fairly dormant until they get within that range. They're just frozen chunks of ice and rock drifting through space. 3I divided by Atlas was already active at 6 to 9 astronomical units from the Sunday. The TESS Space Telescope, which normally looks for exoplanets, captured observations of 3I divided by Atlas when it was still incredibly far from the Sunday. And even at that distance, the object was producing dust. It had a visible coma. It was already behaving like an active comet. That's not supposed to happen with water ice. At 6 to 9 AU, the sunlight is way too weak to sublimate water ice in any significant amount. So something else must be driving the activity. Probably carbon dioxide? Maybe carbon monoxide. These more volatile compounds can sublimate at greater distances. But here's the thing. The amount of activity observed at those distances was significant. Not just a little bit of gas and dust, enough that telescopes could detect it clearly. That requires substantial mass loss. For comparison, most comets at that distance are completely dormant. You'd have to actively look with powerful telescopes just to see them as faint points of light. 3I divided by Atlas was already producing a coma at distances where it should have been dead silent. The Zwicky Transient Facility, which scans the sky for changing objects, actually found pre-discovery images of 3I divided by Atlas going back several months before its official discovery. Those images showed activity extending back to when the object was at 17 AU from the Sunday. 17 astronomical units. That's further out than Uranus. At that distance, sunlight is incredibly weak. The solar flux is less than 0.4% of what Earth receives, and yet 3I divided by Atlas was already active. This suggests either an internal heat source, which seems unlikely for a comet, or compositional differences so extreme that even minimal heating triggers substantial outgassing. The early activity, combined with the carbon dioxide dominance we talked about earlier, paints a picture of an object with chemistry unlike anything in our solar system. Comets from our solar system's Oort cloud, which is the distant reservoir of icy bodies surrounding our sun, have certain chemical signatures. They formed in the outer regions of our solar nebula about 4.6 billion years ago. Their composition reflects the conditions present during our solar system's birth. Comets from the Kuiper belt, which is closer in but still beyond Neptune, have slightly different compositions. They formed in a different region with slightly different temperatures and chemical abundances. We can tell where a comet came from based on its chemistry. It's like a chemical fingerprint. 3I divided by Atlas's chemical fingerprint doesn't match anything from our solar system. Not Oort cloud comets, not Kuiper belt objects, not Jupiter family comets, nothing. Its chemistry points to formation in a high radiation, high temperature environment. Somewhere with conditions that would typically be associated with stellar nurseries or the aftermath of violent stellar events, not the cold outer regions of a protoplanetary disk where comets normally form. The carbon dioxide dominance, the presence of compounds like carbonyl sulfide, the unusual isotopic signatures including carbon-13, all of this points to an origin environment radically different from anything in our cosmic neighborhood. An environment that existed billions of years ago, in an era of the galaxy when things worked differently, which raises a deeply unsettling question. If the early universe produced objects with chemistry this alien to us, what else is out there? How many other ancient wanderers are drifting through the galaxy carrying secrets from cosmic epochs we barely understand? And more immediately, what happens when 3I divided by Atlas gets even closer to the sun and really starts heating up? Part 6. The Close Approach. Right now, as I'm recording this, 3I divided by Atlas is making its closest approach to the Sunday perihelion. The point of closest approach happens on October 30th, 2025. At that point, 3I divided by Atlas will be 1.4 astronomical units from the Sunday. That's actually further than Earth's orbit, which is at 1 AU by definition. So 3I divided by Atlas isn't getting super close to the Sunday. It's not going to become a spectacular naked eye comet or anything like that, but it's close enough that we're getting unprecedented observations, and close enough that the object's behavior is changing dramatically. On October 3rd, 2025, just a few weeks before perihelion, 3I divided by Atlas passed within 17 million miles of Mars. That's actually pretty close in cosmic terms. Close enough that multiple Mars orbiters and the Perseverance rover were able to observe the comet. NASA's Mars Reconnaissance Orbiter captured high-resolution images. The European Space Agency's Mars Express tracked the comet's trajectory. The Emirates Mars mission, HOPE, added its observations. Even the Indian Space Research Organization's Mangalan got some data. And down on the surface, Perseverance pointed its cameras at the sky and captured images of this ancient visitor passing overhead. These observations represent humanity's closest look at an interstellar object ever. Oumuamua shot through our solar system so fast that we barely had time to observe it before it was gone. By the time we realized what it was already past Earth and heading away. 2I divided by Borisov gave us more warning and more time, but it never got particularly close to Earth or any other planet. 3I divided by Atlas is different. Its trajectory brought it near Mars at just the right time when we have multiple spacecraft in the area. And the data they're collecting is incredible. High-resolution images show details of the nucleus structure. Spectrographic analysis reveals exactly what chemicals are being produced as the comet heats up. Multiple spacecraft from different positions allow for stereoscopic observations that reveal the three-dimensional structure of the coma. We're learning more about 3I divided by Atlas with each passing day. But we're also watching something that's kind of disturbing. As the comet heats up, the nickel production is increasing. Remember that pure nickel without iron that shouldn't exist? It's getting stronger. The emission rate has increased as 3I divided by Atlas gets closer to the Sunday. At the same time, the color change is becoming more pronounced. The green coloration is intensifying, indicating increased production of cyanide and other carbon-based molecules. The coma is expanding. That massive carbon dioxide cloud is growing larger and more diffuse. Material that's been frozen for billions of years is suddenly being liberated into space. And here's the thing, every time material sublimates off the nucleus, we lose it. Once those molecules are released into space, they disperse, and we can't study them in their original context anymore. 3I divided by Atlas is essentially evaporating, slowly but steadily. Each day that passes, we're losing a little bit more of this ancient time capsule. Scientists are working frantically to collect as much data as possible before the object moves out of range. Ground-based telescopes, space telescopes, planetary probes, everything that can be pointed at 3I divided by Atlas is being used. But there's only so much they can learn remotely. What they really want is a sample. Imagine if we could send a spacecraft to 3I divided by Atlas, land on its surface, and collect pristine material from its interior. Material that formed in the early galaxy and has remained unchanged for billions of years. We could analyze it in laboratories with techniques that far exceed what we can do with remote spectroscopy. We could definitively answer questions about its age, its composition, its origin. We could potentially learn things about the early universe that we can't learn any other way. But that's not going to happen. 3I divided by Atlas is moving way too fast. Its trajectory wasn't predictable far enough in advance to plan a mission. Even if we started building a spacecraft today, by the time it was ready to launch, 3I divided by Atlas would be long gone. This is a one-time observation opportunity. We get to study it from a distance for a few months, and then it leaves forever. Which brings me to the most emotionally challenging aspect of this whole story. The dying witness. Think about what 3I divided by Atlas represents for a moment. Really think about it. This object is potentially 7 to 14 billion years old. It formed when the universe was radically different from today. The Milky Way galaxy was still young and violent. Stars were being born and dying at rates far higher than we see now. The chemical composition of the galaxy was different. The very physics of star formation and planetary system development operated under conditions that don't exist anymore. 3I divided by Atlas is a direct sample from that era. It's not a photograph, it's not a light echo, it's not a distant observation of something billions of light years away. It's a physical object that was there, that formed during those conditions, and that carries that ancient information locked in its structure. It's a witness, and witnesses are valuable. Think about how much effort historians put into finding first-hand accounts of historical events. Primary sources are precious because they provide direct evidence of what happened, unfiltered by later interpretation or memory. 3I divided by Atlas is a primary source for the early universe. Except this witness is dying. Not in a dramatic way. It's not going to explode or collide with anything. But as it heats up from solar radiation and sublimates away, the information it carries is being lost. The pristine interior is being exposed and degraded. The ancient ices are evaporating into space. And in a few months, it will be gone forever. By March 2026, 3I divided by Atlas will cross Jupiter's orbit and begin its final journey back to interstellar space. It will eventually leave the sun's influence entirely and return to wandering the galaxy. But it will never come back to our solar system. Never. The odds of an interstellar object returning are essentially zero. This is humanity's only chance to study this particular messenger from the cosmic past. And here's what really gets to me. We almost missed it entirely. 3I divided by Atlas could have passed through our solar system undetected. It's not particularly bright. If it had followed a slightly different trajectory, one that didn't bring it close to Earth or Mars, we might never have noticed it. How many other ancient wanderers have passed through our solar system without us seeing them? How many messages from the early universe have we missed simply because we weren't looking in the right place at the right time? The Vera C. Rubin Observatory estimates that interstellar objects of this size pass through our solar system only once every few years, and that's just the ones large enough to detect. Smaller objects probably come through more frequently, but they're too faint for our telescopes to spot. Each one carries information. Each one is a time capsule from wherever it formed. Each one could teach us something new about the universe. But we're only catching a tiny fraction of them. And even when we do detect them, our ability to study them is limited by time and distance. 3I divided by Atlas is the best studied interstellar object so far. We've thrown more resources at it than Oumuamua, or 2I divided by Borisov. Multiple space agencies are collaborating. The best telescopes in the world and in space are being used. And still, there are fundamental questions we can't answer. Questions that would require a sample return mission or at least a close flyby with a dedicated spacecraft. What's the isotopic composition of the interior? Exactly what organic molecules are present? What's the crystalline structure of the ices? Are there any amino acids or other prebiotic compounds? What does the nucleus look like up close? These questions will remain unanswered. The data we're collecting is valuable, but it's incomplete. It's like trying to understand an ancient civilization by looking at it from across a valley with binoculars. You can see the general structure, make some inferences, but you're missing all the fine details that would really tell the story. And the clock keeps ticking. Every day, 3I divided by Atlas moves further away from the inner solar system. Every day, our telescopes have to work a little harder to collect data. Every day, the opportunity window gets a little smaller. By early 2026, it will be too far and too faint for detailed observations. It will fade from visibility, becoming just another faint point of light indistinguishable from background stars. And then it will be gone. The witness will have passed through, briefly testified, and then disappeared back into the darkness from which it came. Future generations will know that 3I divided by Atlas existed because we documented it. They'll have our data, our images, our spectroscopic measurements, but they'll never have a chance to study it themselves. They'll never be able to follow up with new techniques or better instruments. This is it. This brief window in late 2025 and early 2026 represents humanity's entire opportunity to examine this particular piece of the ancient cosmos. And that reality is difficult to accept. It creates a sense of urgency that's rare in astronomy. Usually, if you miss an observation window, you can try again next year or next decade. The stars will still be there. The galaxies will still be there. But interstellar objects don't wait. They pass through once and only once, which is why scientists are so desperate to understand what 3I divided by Atlas is telling us before it's too late. And that brings us to the interpretations. The attempts to make sense of all these anomalies, interpretations, and implications. So let's put all the pieces together. We have an object that, produces pure nickel without corresponding iron, suggesting chemistry that looks industrial, has extreme carbon dioxide dominance unlike any comet in our solar system, is 7 to 14 billion years old, making it potentially older than our entire solar system, travels at 58 kilometers per second, the fastest interstellar visitor ever recorded, measures about 11 kilometers in diameter with a mass around 33 billion tons. Started showing activity at 6 to 9 AU, way further out than expected. Has an anti-tail that seems to violate normal cometary physics. Changed color from red to green as it heated up. Came from the Milky Way's thick disk, a population of ancient stars. Each one of these characteristics, taken alone, might be explainable. Maybe it's just an unusual comet. Maybe there are rare formation scenarios we haven't considered. But taken together, the combination is deeply problematic for our current models. Let's start with the most conservative interpretation. 3I divided by Atlas is a natural comet that formed under extreme conditions in the early galaxy. The chemistry looks weird because the early universe had different chemical abundances and different radiation environments. The velocity is high because it experienced multiple gravitational encounters over billions of years. The size is large because maybe large objects were more common in early planetary systems. The early activity is due to unusually volatile composition. That's the interpretation that most scientists are comfortable with right now. It requires revision of some models and acknowledgement that the early universe was more diverse than we thought, but it doesn't break any fundamental laws of physics. However, there are aspects of 3I divided by Atlas that even this conservative interpretation struggles to explain. The nickel without iron problem is really difficult. Yes, maybe there are exotic nucleosynthetic processes in the early universe that we don't understand. Maybe there are stellar environments that can preferentially produce nickel. Maybe there's some weird chemistry happening on the comet's surface that's masking the iron signature. But all of those explanations require reaching for scenarios that are either speculative or unprecedented. We've never observed natural processes that produce pure nickel without iron. Never. Not in any astronomical object anywhere in the universe that we've studied. The fact that this signature exists on 3I divided by Atlas, and that it's being described as similar to industrial production by respected astrophysicists, should make us pause. I want to be very clear here. I'm not saying 3I divided by Atlas is an alien spacecraft. That's not the point. The point is that the chemistry observed doesn't fit into our current framework of how natural cosmic processes work, which means one of two things. Either natural cosmic processes in the early universe were far more diverse and exotic than we currently understand, or we're seeing something else entirely. Avi Loeb, the Harvard astrophysicist I mentioned earlier, has been vocal about keeping all possibilities on the table. He's not saying 3I divided by Atlas is definitely artificial, but he is saying that the evidence warrants serious consideration of non-natural origins. His argument goes something like this. We have one example of technological civilization capable of producing refined metals. Us. We know that technological civilizations can exist. We know they can create objects with unusual chemistry. We know they can potentially send objects into interstellar space. Given that we know technology is possible, and given that we're observing chemistry that looks industrial, shouldn't we at least investigate whether 3I divided by Atlas might be artificial? Most scientists disagree with that approach. They argue that we should exhaust all natural explanations before even considering artificial ones. And I get that. The burden of proof for claiming something is artificial is extremely high, and rightly so. But here's the uncomfortable reality. If 3I divided by Atlas were artificial, What would we expect to see that we're not already seeing? It's not transmitting radio signals. It's not changing course. It's not displaying any obvious signs of intelligence or purpose. It's just a tumbling object moving through space, outgassing as it heats up. So, if it were some kind of ancient probe or artifact from a long-dead civilization, it would look pretty much exactly like it does now. A dead object, coasting through space for billions of years, slowly degrading and evaporating as it passes near stars. The only anomaly would be its composition. And that's exactly what we're seeing. Chemistry that doesn't fit natural models. Now, I need to emphasize again, this is speculation. There is no definitive evidence that 3I divided by Atlas is artificial. The mainstream scientific consensus is that it's natural, just very unusual. But the conversation itself is significant. The fact that respected scientists are even discussing the possibility tells you how far outside the normal range 3I divided by Atlas sits. And there's another interpretation that's even more unsettling than the artificial hypothesis. What if 3I divided by Atlas is natural, but its existence reveals that the early universe operated according to principles we fundamentally don't understand? What if the chemistry we're seeing, the nickel without iron, the extreme CO2 dominance, the early activity? What if all of that is actually normal for objects that formed 10 billion years ago in the thick disk of the galaxy? What if the early universe was so different, so alien, that its products appear impossible to us because we're interpreting them through the lens of modern astrophysics? Think about that for a second. We've built our entire understanding of the universe based on observations of things that exist now. We look at stars, galaxies, planets, comets, asteroids, all of which formed within the last few billion years in a universe that has settled into relatively stable patterns. But the early universe was different, dramatically different. Star formation rates were higher. Metallicity was lower. The cosmic microwave background radiation was hotter. The expansion rate of the universe was faster. The distribution of dark matter was different. Every single physical condition was different. So why would we expect objects from that era to follow the same rules as objects from the modern era? Maybe pure nickel production without iron was possible back then. Maybe CO2-dominated comets were common in the early galaxy. Maybe formation and ejection processes existed that simply don't occur anymore because the conditions required for them no longer exist. If that's true, then 3I divided by Atlas isn't just an anomaly. It's a revelation. It's evidence that the universe has a history far more complex and strange than we imagined. It means there are entire categories of cosmic phenomena that we've never seen because they only existed billions of years ago. And if that's the case, then every interstellar visitor we detect might potentially be carrying information about extinct cosmic processes. Each one might be a fossil from an era of the universe that was fundamentally different from today. That's almost more unsettling than the artificial hypothesis. Because it means the universe itself is stranger than we thought. It means our models are missing huge pieces. It means that when we look out at the distant early universe with our telescopes, we're not seeing the full picture because we're missing entire categories of objects and processes that don't exist anymore. 3I divided by Atlas might be proof that the early cosmos harbored environments and events so extraordinary that their products appear impossible when viewed through modern astronomical frameworks. And we're about to lose our best evidence of that fact. Part 3. What we're losing. Let's talk about what happens next. 3I divided by Atlas will reach perihelion on October 30th, 2025. For a few weeks around that date, it will be at peak brightness and peak activity. Every telescope that can observe it will be collecting data. Then it will start moving away. By late November, it will be noticeably fainter. By December, only the most powerful telescopes will still be able to get useful observations. By January 2026, it will be very difficult to observe. And by March, it will cross Jupiter's orbit and be effectively lost to us. After that, 3I divided by Atlas will continue on its trajectory out of the solar system. It will cross the orbit of Neptune, then the Kuiper belt, then eventually reach the Oort cloud boundary. Years from now, it will exit the sun's gravitational influence entirely and return to interstellar space. And that will be it. Humanity's brief encounter with this ancient messenger will be over. The data we collected will be analyzed for years. Scientists will publish papers. Theoretical models will be updated. We'll learn as much as we possibly can from the observations. But there will always be questions left unanswered. There will always be mysteries we couldn't quite solve because we couldn't get close enough or couldn't study it long enough. And here's the really frustrating part. We know these objects are out there. 3I divided by Atlas isn't unique. There are probably millions or billions of ancient interstellar wanderers drifting through the galaxy, each one potentially carrying information from different epochs, different environments, different formation scenarios. But we only get to study the tiny fraction that happened to pass through our solar system. And even then, only the ones we happen to detect in time. The Vera C. Rubin Observatory, when it becomes fully operational, will dramatically increase our detection rate. It's designed to scan the entire visible sky every few nights, looking for anything that changes or moves. It should catch interstellar visitors much earlier in their approach, giving us more time to study them. But even with improved detection, we're still limited to remote observation. We can point telescopes at these objects, analyze their light, measure their trajectories, but we can't touch them. We can't sample them. We can't examine them up close. To do that, we'd need dedicated interstellar object intercept missions. We'd need spacecraft designed to rapidly launch and rendezvous with fast-moving targets. We'd need propulsion systems capable of matching velocities with objects traveling at tens of kilometers per second. That technology doesn't exist yet. We're working on it. Concepts have been proposed, but nothing is ready. So when 3I divided by Atlas leaves, we have to accept that we got the best data we could with the tools we have. And that has to be enough. But it's not really enough, is it? Because 3I divided by Atlas represents something profound. It's not just a comet. It's not just a scientific curiosity. It's a message from a version of the universe that no longer exists. It's physical evidence of conditions and processes that we can barely imagine. And we're letting it slip away because we don't have the capability to do anything else. Future generations might look back on this moment with frustration. They'll see that we detected 3I divided by Atlas, that we recognized its significance, that we understood it was carrying invaluable information. But we couldn't capture it, couldn't preserve it, couldn't extract the full knowledge it was offering. It's like finding an ancient manuscript written in a language you partially understand, knowing it contains lost wisdom, but only getting to glance at a few pages before it crumbles to dust in your hands. That's what makes this story emotionally difficult. It's a story about limits. The limits of our technology, the limits of our timing, the limits of what we can learn from these fleeting encounters with the cosmic past. 3I divided by Atlas won't be the last interstellar visitor, but it might be the most significant one we see for decades. And by the time the next one arrives, will we be any better prepared? Will we have the spacecraft ready? Will we have the missions designed? Will we have the political will and funding to actually intercept and study these objects properly? Or will we just watch the next one pass by too, collecting what data we can from a distance, knowing we're missing the full picture? These are questions we need to grapple with, because 3I divided by Atlas is showing us what's possible. It's showing us that the universe has secrets traveling through it. Ancient secrets, profound secrets. Secrets that could reshape our understanding of cosmic history. But secrets that are useless if we can't access them. What this means. So let's step back and think about what 3I divided by Atlas really means for our understanding of the universe. First, it confirms something that some scientists suspected but many were uncertain about. The galaxy has a population of ancient objects that formed under conditions radically different from today. These objects are out there, wandering between stars, occasionally passing through solar systems like ours. Before 3I divided by Atlas, we could theorize about such objects. Now we know they exist. We've seen one. We've measured it. We've analyzed its chemistry. It's real. Second, it reveals that our models of comet formation, stellar nucleosynthesis, and planetary system evolution are incomplete. They work well for objects in the modern universe, but they break down when applied to objects from the early galaxy. That's not a failure of science. It's an opportunity. It tells us where we need to focus our efforts, what questions we need to ask, what observations we need to make. Third, it demonstrates that interstellar visitors can be scientifically valuable in ways we didn't fully appreciate before. Oumuamua was interesting because it was the first 2I divided by Borisov. Was interesting because it confirmed interstellar comets exist. But 3I divided by Atlas is interesting because of what it's teaching us about the early universe. Each interstellar object is potentially a unique sample from a different stellar system, a different era, a different environment. They're not just rocks passing through. They're archives of cosmic information. Fourth, and perhaps most importantly, 3I divided by Atlas reveals that the universe has surprises left. Despite all our telescopes, all our observations, all our sophisticated models, we can still encounter things that genuinely puzzle us, things that don't fit, things that challenge our understanding. That's both humbling and exciting. Humbling because it reminds us how much we still don't know. Exciting because it means discovery is still possible. We haven't figured everything out. The universe can still astonish us. The specific mysteries of 3I divided by Atlas might be resolved eventually. Maybe future observations of other interstellar objects will provide context. Maybe new theoretical work will explain the chemistry. Maybe we'll eventually understand how objects like this form and why they display the characteristics they do. But right now, in this moment, 3I divided by Atlas is a genuine cosmic enigma, and that's special. In an age where we can answer so many questions with a quick internet search, where satellites map every inch of Earth, where we've sent probes to the outer reaches of the solar system, genuine mysteries are rare. 3I divided by Atlas is one of those rare mysteries, and we're living through the brief window when it's accessible to study. What conclusions can we draw? 1. The early universe was more diverse and complex than we currently understand. Objects from that era can have chemistry and characteristics that seem impossible by modern standards. 2. Interstellar space is not empty. It's filled with wandering objects from countless stellar systems, each carrying information about its origin. 3. We need better tools and capabilities to study these objects. Remote observation is valuable but insufficient. We need interception capabilities. 4. Time matters. The window to study interstellar visitors is always brief. We need rapid response protocols and prepared missions. 5. Humility is essential. When we encounter something we don't understand, the first step is admitting that we don't understand it, not forcing it into existing models, not dismissing anomalies, but really looking at what the data is telling us, even if it's uncomfortable. 3i divided by Atlas has taught us all of these lessons, and it's still teaching us. Every new observation adds to the picture. Every analysis reveals something new, but the clock is ticking. The final message. There's something deeply poignant about 3i divided by Atlas's journey. Think about it from the object's perspective, if such a thing makes sense. It formed billions of years ago in a part of the galaxy we can only see through powerful telescopes. It coalesced from gas and dust around a star that might not even exist anymore. It was part of a planetary system that has long since been disrupted or destroyed. Then, through some violent event or series of events, it was ejected, flung out into the vast emptiness between stars, and it began wandering. For billions of years, it drifted through the galaxy. It passed by stars. Maybe it passed through other solar systems, unseen by any inhabitants who might have been there. It crossed nebulae when new stars were being born. It skirted the edges of stellar nurseries where planetary systems were forming. All the while, it remained frozen, unchanged. A chunk of ancient ice and rock carrying information from the era when it formed. And then, in October 2025, its path happened to intersect with our solar system. For the first time in its unimaginably long journey, it was noticed. A small species on a small planet in this random stellar system happened to have developed technology capable of detecting it. They pointed their instruments at it. They analyzed its light. They tried to understand what it was and where it came from. And then, after just a few months, it will continue on. Back out into the darkness. Back to wandering the galaxy, perhaps for billions more years, until it eventually breaks apart or collides with something or falls into a star. From 3i divided by Atlas's perspective, if it had one, this encounter with humanity is the briefest moment. A fraction of its existence. We're just one of countless stellar systems it's passed through. But from our perspective, this is significant. This is a once-in-a-lifetime event. An opportunity to touch, however briefly, something from the deep past of the universe. It's a reminder of scale, the cosmic scale of time and space that we live in, the incredible age of the galaxy, the vast distances between stars, the tiny sliver of time that human civilization has existed compared to the age of the universe. 3i divided by Atlas existed for billions of years before humans walked the Earth. It will continue to exist long after humans are gone, assuming we don't survive as a species for millions or billions of years into the future. We're witnessing a passing moment in the life of something nearly eternal. And that perspective shift is important. It reminds us that we're not the center of the cosmic story. We're participants in something much larger and older than ourselves. But here's the beautiful paradox. Even though we're tiny and brief compared to the cosmic scale, we matter. Because we're the ones asking questions. We're the ones trying to understand. We're the ones who saw 3i divided by Atlas not just as a rock passing through space, but as a messenger carrying information worth decoding. That curiosity, that drive to understand, that's uniquely human as far as we know. Maybe there are other species out there asking similar questions about their universe. Maybe they've detected their own ancient wanderers and puzzled over the same kinds of mysteries. But in our corner of the galaxy, in this moment, we're the ones doing it. And that's meaningful. 3i divided by Atlas won't remember us. It can't, but we'll remember it. The data we've collected will exist in archives, papers will be published. Students decades or centuries from now will study this object as part of the history of astronomy. And maybe, just maybe, what we learn from 3i divided by Atlas will help us understand the next interstellar visitor, and the one after that. Each object building on the knowledge from the previous ones. Each encounter teaching us a little bit more about the universe we inhabit. That's how science works. Incremental progress. Building knowledge piece by piece. 3i divided by Atlas is one piece of a much larger puzzle. An important piece. A surprising piece. But still just one piece among many. The bigger picture that's emerging is this. The universe has a history. Not just a history of cosmic expansion and galaxy formation and star birth, which we can observe through telescopes looking at distant objects, but a material history. A history written in physical objects that have survived from ancient epochs. These objects are traveling through space right now, ancient wanderers from the early universe, witnesses to cosmic events that happened billions of years ago, each one potentially carrying unique information about conditions that no longer exist. 3i divided by Atlas is showing us that this archive exists, and that it's accessible, at least partially, if we're paying attention and have the tools to detect and study these objects. That opens up a whole new way of studying cosmic history. Instead of just looking at distant light from ancient galaxies, we can potentially examine actual material from the early universe that happens to pass through our solar system. It's like the difference between reading about ancient Rome in history books versus excavating actual Roman artifacts. The artifacts provide a directness and tangibility that written descriptions can't match. 3i divided by Atlas is that artifact. And interstellar objects in general represent an archive of physical samples from across the galaxy and across cosmic time. We're only just beginning to understand how to use this archive, how to detect these objects early enough, how to analyze them effectively, how to extract the maximum information from brief observation windows. But we're learning. And 3i divided by Atlas is teaching us the bigger questions. Let's talk about some of the bigger questions that 3i divided by Atlas raises. Questions that go beyond the specific chemistry or age of this one object. First question, how common are objects like this? 3i divided by Atlas is the third interstellar visitor we've detected in 8 years. That's not a huge sample size, but it suggests that these objects are passing through the solar system relatively frequently. We're probably missing most of them because they're too small or too faint to detect with current instruments. If large objects like 3i divided by Atlas come through every few years, and if smaller objects come through even more frequently, then at any given moment there might be multiple interstellar objects within our solar system that we simply haven't detected yet. That's a strange thought. Right now, somewhere beyond Saturn or Uranus, there might be another ancient wanderer passing through. We just don't see it because it's not bright enough or we're not looking in the right direction. The galaxy might be full of these objects, billions or trillions of them, ejected from their home systems and wandering between the stars. Most of them will never be observed by anyone. They'll drift forever through the void, carrying their secrets with them. But occasionally, one will pass through a system like ours where someone is watching. And for a brief moment, that object's story intersects with ours. Second question, what does this tell us about the frequency of planetary systems in the early galaxy? Every interstellar object had to come from somewhere. They form in planetary systems and then get ejected. The fact that we're detecting these objects at all suggests that planetary systems have been common throughout the galaxy's history. 3i divided by Atlas formed in a planetary system that existed 7 to 14 billion years ago. That's incredibly early in galactic history. It means planetary systems were forming and evolving even in that ancient era. Some scientists thought that early planetary systems might be rare because the metallicity of the early universe was lower. Planets need heavy elements to form, and those elements were scarcer in the early universe. But if objects like 3I divided by Atlas are evidence of early planetary systems, then maybe planet formation was more robust than we thought. Maybe planets have been forming around stars for almost the entire history of the galaxy. And if planets have been that common for that long, what about life? What about intelligent life? What about technological civilizations? This is where things get really speculative, but follow the logic. If planetary systems have existed for 10+ billion years, that's a lot of time for life to evolve. A lot of time for intelligence to emerge. A lot of time for civilizations to rise and fall. Could 3I divided by Atlas have passed through systems that harbored life? Maybe even intelligent life. Maybe even technological civilizations that saw this object pass through their sky, just as we're seeing it pass through ours. We'll never know, but it's possible. And that adds another layer of meaning to 3I divided by Atlas's journey. Third question. What happened to the system that 3I divided by Atlas came from? The object was ejected violently. Something had to provide the energy to fling a 3 billion-ton object out of its home system at high velocity. What was that event? Maybe the star that 3I divided by Atlas originally orbited went supernova. The shockwave and gravitational disruption could have ejected material from the system. Maybe the system was in a dense stellar cluster, and a close encounter with another star gravitationally scattered all the planets and debris. Maybe the system formed in a binary or multiple star arrangement, and the complex gravitational dynamics led to instabilities that ejected large amounts of material. We don't know, but whatever happened, it was violent enough to destroy or dramatically alter the original planetary system. That system no longer exists in any recognizable form. The star might still be there, but the planets are gone, scattered to the galaxy. 3I divided by Atlas is one survivor of that ancient catastrophe. And that raises an uncomfortable thought. Solar systems can be destroyed. Our solar system has been stable for 4.6 billion years, but that's no guarantee it will remain stable forever. Gravitational perturbations, close stellar encounters, changes in the galaxy's structure. Any number of things could eventually disrupt our solar system too. And if that happens billions of years from now, pieces of Earth, or Mars, or Jupiter's moons might end up as interstellar wanderers themselves. Future civilizations in distant solar systems might detect a chunk of Earth passing through their neighborhood. They might analyze its chemistry and wonder about the planet it came from. They might puzzle over the unusual isotopic signatures and try to figure out what kind of environment could have produced them. They'd be studying our world long after humans are gone, through a fragment that survived the death of our solar system. That's the fate that befell 3I divided by Atlas's home. And it could be the fate of our home too, given enough time. Fourth question. Should we be worried? Some people have asked whether 3I divided by Atlas poses any danger to Earth. The answer is no. Its trajectory doesn't bring it anywhere near Earth. It passed Mars at a safe distance and will continue on its path without threatening any planet. But the question raises a valid point. Could an interstellar object ever pose a threat? Technically, yes. If an interstellar object happened to be on a collision course with Earth, it would be moving much faster than typical asteroids or comets from our solar system. The impact energy would be correspondingly higher. However, space is really, really big. The odds of an interstellar object randomly hitting Earth are astronomically small, much smaller than the odds of being hit by a solar system asteroid or comet, which are already very small. So, no, we shouldn't be worried about interstellar objects as an impact threat, but we should be interested in them for what they can teach us. Fifth question. What's the best case scenario for future interstellar object research? Ideally, we develop the capability to send spacecraft to intercept these objects. Not just observe them from Earth, but actually fly alongside them, land on them, and collect samples. The technology to do this is challenging, but not impossible. We'd need fast response launch capabilities. We'd need high-performance propulsion systems. We'd need spacecraft designed for rapid deployment and long-duration missions. Some concepts have been proposed. One idea is to have a spacecraft sitting ready on Earth, fueled and prepared, that can launch within weeks of detecting an interstellar object. It would use a high-speed trajectory to catch up with the object while it's still in the inner solar system. Another idea is to have multiple small spacecraft already in space, positioned at various points in the solar system, ready to redirect toward any interstellar object that's detected. These ideas are technically feasible. They just require funding and political will. If we could intercept an interstellar object like 3I divided by Atlas, the scientific payoff would be enormous. We could answer definitively questions about its composition, age, and origin. We could search for organic molecules and prebiotic compounds. We could examine the surface structure and interior layers. We could potentially learn things about the early universe that we can't learn any other way. That's the future we should be working toward. Not just detecting and observing these objects from a distance, but actively engaging with them, treating them as the valuable scientific resources they are. What comes next? So, what actually happens now? What's the immediate future for 3I divided by Atlas research? Over the next few months, as the object moves away from perihelion and starts heading back out of the solar system, scientists will continue collecting data as long as it's feasible. Every observation adds to our understanding. The data already collected will be analyzed in detail. Teams around the world are working on papers right now, preparing to publish their findings. These papers will go through peer review and eventually be added to the scientific literature. Some of the questions about 3I divided by Atlas will be answered through this analysis. The exact composition of the coma, the rotation rate of the nucleus, the production rates of various molecules as a function of distance from the sunday, the detailed structure of the dust distribution. Other questions will remain open. The interior composition, the formation mechanism, the exact origin point. These might be answered partially through modeling and comparison with other objects, but definitive answers would require sample return. In the years following 3I divided by Atlas's departure, astronomers will be watching for the next interstellar visitor. The Vera C. Rubin Observatory will begin full operations soon, dramatically increasing our ability to detect these objects early. When the next one is found, we'll apply lessons learned from 3I divided by Atlas. We'll know to look for certain chemical signatures. We'll know to check for early activity. We'll know to measure the nickel to iron ratio. We'll have a framework for understanding these objects that we didn't have before. Each interstellar visitor will add to that framework. Over time, we'll build up a catalog of these objects. We'll start to see patterns. Maybe we'll find that some come from the galactic thick disk like 3I divided by Atlas, while others come from different populations. Maybe we'll find that certain chemical signatures correlate with certain galactic origins. Eventually, we'll have enough data to start making statistical arguments about the frequency of different types of interstellar objects, about the typical ejection mechanisms, about the diversity of planetary systems across the galaxy and across cosmic time. 3I divided by Atlas is the beginning of that process. It's providing a data point that future observations will build on. But beyond the specific scientific outcomes, 3I divided by Atlas is having another effect. It's capturing public imagination. It's making people think about the vast scales of time and space that our universe operates on. It's raising questions about our place in the cosmos and about what else might be out there. That's valuable too. Science isn't just about accumulating data, it's also about inspiring wonder and curiosity. It's about helping people see the universe as a place full of mysteries worth exploring. 3I divided by Atlas is definitely mysterious. And the fact that mainstream media is covering it, that people are talking about it, that videos like this one exist, that's all part of the impact this object is having. It's making people look up at the night sky and wonder what else is passing through. What other ancient travelers are out there carrying secrets from the deep past of the universe. And maybe, just maybe, it's inspiring some young person somewhere to pursue astronomy or planetary science or aerospace engineering. Maybe someone watching this video will be part of the team that designs the first interstellar object intercept mission. That's how progress happens. One discovery inspires the next generation, who build the tools and ask the questions that lead to the next discovery. 3I divided by Atlas is part of that chain, a link connecting our current understanding to whatever we'll discover next. The worst fear confirmed. So let's come back to the title of this video. NASA's latest data confirms everyone's worst fear. What exactly is that fear? It's not that 3I divided by Atlas is dangerous. It's not that it's an alien spacecraft. It's not even that it's going to reveal something that breaks physics. The worst fear that 3I divided by Atlas confirms is much more subtle and much more profound. It's the fear that the universe operates according to principles we don't fully understand. That despite all our scientific progress, despite all our sophisticated models and powerful telescopes, we're still missing huge pieces of the puzzle. 3I divided by ATLAS shows us chemistry that shouldn't exist according to our current understanding of nucleosynthesis. It shows us behavior that doesn't fit our models of cometary activity. It shows us an object that challenges multiple assumptions we've made about how the universe works. And the scary part isn't the specific anomalies, it's what they imply. They imply that the early universe was far stranger than we imagined. That cosmic history includes epochs where things operated differently. That the processes we observe today are just a subset of the processes that have occurred over the universe's 13.8 billion year history. If that's true, then we're in a position similar to archaeologists trying to understand ancient civilizations while only having access to modern artifacts. We're trying to understand the full scope of cosmic history while only being able to directly observe the most recent chapter. 3I divided by Atlas is giving us a glimpse of an earlier chapter, and what we're seeing doesn't match our expectations. It's forcing us to revise our understanding, to acknowledge that we don't know as much as we thought we did. That's uncomfortable. Scientists generally don't like being wrong. Nobody does. But it's also exciting because it means there's still so much to discover. The worst fear is also about time and opportunity. We have this ancient messenger passing through our solar system right now. It's offering to teach us about the early universe, but only if we can figure out how to read its message. And we only have a few months before it's gone forever. What if we miss something crucial? What if there's a key piece of information locked in 3I divided by Atlas's composition that we fail to detect because we're not looking for it or don't have the right instruments? What if future scientists look back at this moment and realize we had the opportunity to answer a fundamental question about the universe, but we missed it? That possibility is genuinely frightening for anyone who cares about knowledge and discovery. The idea that we might be on the cusp of understanding something profound, but the window closes before we figure it out. It's like being handed an ancient text in a partially understood language, knowing it contains important information, but only having a few days to translate it before it disintegrates. That's the situation we're in with 3I divided by Atlas. And more broadly, it's the situation we're in with all interstellar objects. They pass through so quickly. We have such limited time to study them. The knowledge they carry is irreplaceable, but it's also fleeting. So the worst fear that 3I divided by Atlas confirms is really a combination of things. Fear that the universe is more complex than we understand. Fear that we're missing crucial information. Fear that opportunities for discovery are slipping away. Fear that despite our best efforts, we're still fundamentally limited in what we can know about the cosmos. But here's the thing about fear. It can be motivating. It can drive us to do better, to try harder, to develop better tools and ask better questions. The discomfort of not understanding 3I divided by Atlas fully should motivate us to improve our capabilities, to fund better telescopes, to develop interstellar object intercept missions, to train more scientists to take these opportunities seriously. Because 3I divided by Atlas won't be the last ancient wanderer to pass through our solar system. There will be others. And each one is an opportunity to learn something new about the universe and our place in it. The question is whether we'll be ready, whether we'll have the tools and the knowledge and the preparedness to take full advantage of those opportunities. 3I divided by Atlas is showing us what we're capable of with our current technology. We can detect these objects, we can observe them, we can learn from them, at least partially. But it's also showing us our limitations, what we can't do, what we're missing, where we need to improve. That's valuable feedback. That's information we can use to get better. So while the title talks about confirming worst fears, there's actually a lot of hope in this story too. Hope that we're learning, hope that we're improving, hope that the next time an ancient messenger comes through, we'll be better prepared to hear what it has to say. Final thoughts. I want to leave you with a few final thoughts about 3I divided by Atlas and what it represents. First, appreciate the moment we're living in. Right now, as you're watching this video, there's an object from the early universe passing through our cosmic neighborhood. That's incredible. That's special. That's something that humans 100 years ago couldn't have experienced because they didn't have the technology to detect it. We live in an era where we can discover and study these ancient travelers. That's a privilege. It's easy to take for granted, but we shouldn't. Second, remember that every object in space has a story. 3I divided by Atlas isn't just a rock. It's a time capsule. It's a survivor. It's a witness to cosmic history. When we study it, we're not just measuring chemistry and trajectories. We're uncovering stories. We're reading cosmic archaeology. That perspective makes the science more meaningful. It connects us to the larger narrative of the universe. Third, embrace the mystery. Not everything needs to be explained immediately. Not every question needs an answer right now. Part of what makes 3I divided by Atlas so fascinating is that it's mysterious. It's puzzling. It's challenging our understanding. That's not a bug. It's a feature. Mystery is what drives science forward. If we understood everything, there'd be nothing left to discover. So when you encounter something that doesn't make sense, don't be frustrated. Be curious, ask questions, look for answers, but also appreciate the journey of discovery itself. Fourth, think about scale. 3I divided by Atlas has been traveling for billions of years. Billions. With a B. That's longer than Earth has existed. That's longer than the Sun has existed. That's almost as long as the universe has existed. And during all that time, it's been moving through space, mostly unchanging, waiting for a moment like this when someone would notice it and wonder about its story. We're that someone. We're the ones noticing. We're the ones wondering. That connection across billions of years between an ancient object and modern observers is profound. It's a form of communication across time. The object is telling us about where it came from. If only we can learn to read its message. 5th, consider the implications for life and intelligence in the universe. 3I divided by Atlas passed through a planetary system that formed billions of years ago. That system might have had planets. Those planets might have had oceans and atmospheres. Life might have evolved there. We'll never know. But it's possible. And if life existed in that system, and if it survived long enough, maybe intelligent beings looked up at their sky and wondered about the universe, just as we do. Maybe they asked the same questions we're asking. Maybe they built telescopes and studied the stars. Maybe they wondered if they were alone. And then their system was destroyed or they went extinct. And 3I divided by Atlas is one of the few remnants that survived to tell the tale. That's a humbling thought. It reminds us that nothing is permanent. Civilizations rise and fall. Planets form and are destroyed. Stars are born and die. But the universe goes on. And objects like 3I divided by Atlas carry forward the memory of what came before, even if that memory is locked in chemical signatures and isotopic ratios that require advanced technology to read. 6th, think about responsibility. We have a responsibility to study these objects as carefully as we can, not just for ourselves, but for future generations who will want to know what we learned. We're the ones who happened to be here when 3I divided by Atlas passed through. The burden of extracting knowledge from this opportunity falls on us. Future scientists will work with the data we collect. They'll build on the observations we make. They'll answer questions we can't answer because they'll have better tools and more context. But they can only do that if we do our job now. If we collect the data carefully, if we publish our findings openly, if we preserve the observations for posterity, that's part of the scientific tradition. Each generation builds on the work of the previous generation. We're part of that chain. And finally, remember that this is just the beginning. 3I divided by Atlas is the third interstellar object we've detected. 3, there will be more, many more. Each one will teach us something new. Each one will add to our understanding. Over the coming decades and centuries, as our detection capabilities improve and as more of these objects pass through, we'll gradually build up a comprehensive picture of interstellar space and the diversity of objects traveling through it. We'll learn about different stellar populations, different formation environments, different ejection mechanisms, different cosmic epochs.